These are the sample problems for Math 117, Class 8. I'm going to put the proof, which is the fourth problem, into a separate audio file. So my first task is to prove Bayes' rule, because Deneen doesn't take the time to do it. And here's how. The definition of conditional probability is that when you take P of A conditioned on B and multiply it by the probability of event B, you get the probability of A intersect B. And of course, you can write this the other way around as P of B conditioned on A times P of A. And solving this for the conditional probability P of A conditioned on B, we immediately get P of A times P of B conditioned on A times P of B, which is Bayes' rule. Now, I'm not going to apply it immediately. Instead, I'm going to show you how to compute a conditional probability using an alternative technique, namely considering a smaller sample space. So I'm going to write this probability of P as P of 4 aces conditioned on 2 aces, by which I mean the following. My opponent has a 5-card poker hand face down, exposes 2 cards, they both turn out to be aces. This is the way 5-card stud poker is played. And what I want to know is, does my opponent have all 4 aces? And one way to do that is to say, I'm now considering a probability problem with a smaller sample space, namely the set of all shuffled 50-card decks, 52-card decks minus 2 aces, and what I am doing is selecting 3 cards at random from that deck. And the probability that my opponent has all 4 aces is that the number with all 4 aces has to be divided by the number of 3-card sets. So there are 48 ways that my opponent's unexposed 3 cards can include the 2 missing aces, and there are 50 choose 3 ways of selecting that set of 3 cards, and the ratio is easy to work out. I've got 48 divided by 50 choose 3 as 50 factorial in the denominator, 47 factorial times 3 factorial in the numerator, and that works out to 3 factorial, or 6, over 50 times 49. That's the easy way to do the problem. The hard way to do the problem is to use Bayes' rule. So I can write down Bayes' rule mechanically. Probability of 4 aces given 2 aces is the probability of 2 aces given 4 aces times the probability of 4 aces divided by the probability of 2 aces. Now I have to think about what that means. Probability of 2 aces given 4 aces is the probability that the event 4 aces has occurred. In other words, my opponent has all 4 aces among his 5 cards, and when he reveals 2 cards to me, they're both aces. The probability that the first revealed card is an ace is 4/5. The probability that the second one is one of the 3 aces among the remaining 4 is 3/4. And then I have to multiply by the probability that my opponent was dealt a hand with 4 aces. There are 48 ways that can happen, corresponding to the 46 possible 5th cards, and I have to divide by the number of ways of choosing 5 cards out of 52. That's 52 choose 5. Now for the denominator. What do I mean by the probability of two aces? I mean the probability that the two cards that my opponent exposes are both aces. There are 12 ways that can happen. 4 choices for the suit of the first ace exposed, 3 for the suit of the second one, and there are 52 times 51 ways of choosing a pair of 2 cards from the deck. Now the rest is all algebra. In the numerator, I have 3/5 times 48. In the denominator, I have 4 times 3 over 52 times 51, multiplied by this binomial coefficient from the numerator, which is 52 factorial over 47 factorial times 5 factorial. So I've got 3/5 times 48 times 47 factorial, which is 48 factorial times 5 factorial, over, in the denominator, 52 factorial divided by 52 and 51 to get 50 factorial times 12. That's 3/5 times 120. 50 factorial over 48 factorial is 50 times 49 times 12. And what do you know? I've got 3/5 of 10, which is 6 over 50 times 49. Same answer, but this is a nice example of how Bayes' rule can make the complication more tedious rather than. The next problem is now a very standard counterexample in elementary probability, but remarkably, it was not invented until the 20th century. It comes with a variety of storylines. Here's mine. You've asked the offices of career services to arrange interviews with 3 large firms, Goldman Sachs, Deutsche Bank, and Weiss Asset Management. The last of these employs a former student of mine and is situated on Commonwealth Avenue in the Back Bay. How's this done? The director rolls a tetrahedral die, has 4 faces, labeled G, D, W, and GDW, and arranges interviews with all the firms whose initials come up. The remarkable thing is that these 3 events, though they're pairwise independent, are not independent, because if I look at the probability of the intersection of all 3, it's not the product of the individual probabilities. So let's work out some probabilities. The probability of the event G intersect D intersect W is the probability that the face with GDW comes up. In other words, it's 1/4. The probability of an event like G intersect D is also 1/4, because the only way that can happen is if the GDW face comes up. The probability of getting an interview with one specific company, whichever it may be, is 1/2, because that happens for Goldman Sachs, for example, if either you get the G face or the GDW face. So the events are pairwise independent. The probability of G intersect D and the probability of G times the probability of D are both equal to 1/4. However, the 3 events are not independent, because the probability of G times the probability of D times the probability of W is 1/2 cubed, which is 1/8, which is not equal to the probability of the intersection of the three events. The third of these problems is a rather weird one from Deneen, and I think the point it makes is that two events can be independent kind of by accident. It just so happens that the probability of their intersection is equal to the product of their probabilities. But there's nothing fundamental in the setup of the experiment that's responsible for this. So here's Deneen's example. The sample space is 1, 2, 3, 4, 5, 6. The sigma field consists of all possible subsets of 1, 2, 3, 4, 5, 6. And what we know about the probability measure is that the probability of a 1 is 1/12, the probability of a 2 is 2/12, and so on up through 4. We're also told that the event 1, 2, 5 is independent of the event 2, 3, 6, and that's enough information so we can figure out the probability of 5 and the probability of 6 by getting a pair of simultaneous equations. So here goes. First, let me work out the probability of the event 1, 2, 3, 4. The probability that the number chosen is 1, 2, 3, or 4. And that, of course, is 1/12 for the 1, plus 2/12 for the 2, plus 3/12 for the 3, plus 4/12 for the 4, which is 5, 6. And therefore, the probability of a 5 plus the probability of a 6 is equal to the remaining 1/6. I should probably put these in squiggly brackets, but it's rather a pain to write, so I'm just going to call them P of 5 and P of 6. Now, what about these two events that are given as independent? Well, the probability of getting a 1 or a 2 or a 5 is 1/12 plus 2/12 plus P of 5. The probability of getting a 2 or a 3 or a 6 is 2/12 plus 3/12 plus the probability of getting a 6. And we're told that these two events are independent. The intersection of the two events is the set that contains just 2, and we know that P of 2 is 2 over 12, or 1 over 6. We also know that the probability of 6 from up here is equal to 1/6 minus the probability of 5. So, the probability of this first event, 1/4 plus P of 5, times the probability of this second event, which is 2/12 plus 3/12 plus 2/12 minus P of 5, or 7/12 minus P of 5. For independent events, the probability of those two events multiply out to the probability of their intersection, which we know is 1/6. Now the rest is just algebra. The simplest thing to do is to multiply through by something that will clear the fractions. So I will multiply through by 48. when I multiply through by 48, I get 12 plus 48 times p of 5 times 28 minus 48 times p of 5 is equal to 8. And I just realized I messed that up. I'm not going to start the whole recording again. I'm multiplying by 48 on the left. That means what I want to do is multiply the first factor by 4 and the second factor by 12. That's more like it. 1 plus 4 times p of 5. Then to complete the multiplication by 48, I multiply the second factor by 12. 7 minus 12 p of 5 equals 8. That's more like it. Multiplying this out, I get 48 times p of 5 squared minus 16p of 5 plus 1 is equal to 0. And that factors rather nicely into 12p of 5 minus 1 times 4p of 5 minus 1 is equal to 0. You say, aha, quadratic, 2 solutions. But not quite. This is a probability problem. Probabilities cannot be negative. And if p of 5 were 1/4, that would make p of 6 negative, and therefore the only valid solution is p of 5 is equal to 1/12, which means that p of 6 is also equal to 1/12.